Hello everyone, I am Rathnayake from Department of Civil Engineering, University of Peradeniya. The topic of the paper I am presenting today is large-scale direct shear test on foul ballast to numerical study. Let's get started with the background knowledge. The ballasted truck is most conventional, most economical, and widely used transportation mode in many countries. This is mainly due to the frequent congestion of major highways, which is caused by rapid urbanization, and the ballast layer transmit and distribute the wheel load from sleepers to the underlying subballast and subgrade. And other than transmitting the wheel load, the ballast layer absorb energy and vibration generated from the moving train. Therefore, maintaining the quality of ballast material is important. The figure shows the typical geometry of a ballasted railway track. Upon repeated train loading, ballast become degraded and fouled by the progressive accumulation of fines within the ballast voids. Other than this, ballast is fouled with intrusion of foreign materials such as fine silt, very fine sand and clay, which happens due to various external factors such as floods, winds and mud pumping. When the ballast layer is contaminated with fines, it changes its physical and mechanical properties and then leads to the change of shear strength of ballast layer. In literature, there are many studies done to investigate the ballast properties. Huang et al. In 2019 has measured strength and deformation characteristics of fresh ballast and fouled ballast using a large-scale direct shear device. This study has been based on laboratory tests. The figure shows the direct shear device used, and Ismail et al. Has conducted a study to analyze the effect of sand fouled ballast on train-induced vibrations on means of experimental and numerical methods. For this purpose, a railway track in Iran was being monitored for 6 months. Then a finite element model of the field setup was developed. However, it is seen that in many studies on fouled ballast were conducted in laboratory or field. Limited attempts were done to study the effect of fouling material on ballast numerically. Especially numerical models of laboratory tests to observe ballastic characteristics are rare. So there lies our aim to conduct a study to develop a finite element model to understand the effects of fine materials on the shear behavior of railway ballast material. In order to achieve this aim, we have accomplished the following objectives: a 3D finite element model to simulate large-scale direct shear test for ballast fouled with fine particles was developed. Then a parametric study was done after validating the model. The data required for the validation of the finite element model is obtained from the study done by Navaratnarajah et al. In 2019. This study mainly focuses on influence of different types of fine materials, intrusion on shear and degradation behavior of ballast, and clay and fine sand were used as fouling material. A series of large-scale direct shear tests were performed with and without ballast fouling for different loads, and large-scale direct shear test apparatus has fixed top ring and a movable bottom ring. The vertical load is applied on the top top plate, and tests were done for fresh ballast, for sand fouled ballast with 10% sand and 15% sand, and ballast fouled with 5% clay. 3 vertical load cases of 30, 60, and 90 kilopascals were used. The lateral load was applied to the bottom ring at a constant loading rate of 0.04 millimeters per minute using hydraulic loading system. The horizontal displacement, the vertical displacement, and the horizontal load reading was obtained by the data logger. After understanding the test procedure, the finite element model was developed using finite element software Abacus. The model consists of 3 main parts, namely the upper ring, the lower ring, and the ballast. The ballast is modeled as a continuum. The overall properties of the ballast with fines are considered as one material when assigning material properties to foul ballast. When talking about the boundary conditions, the upper ring is fixed by restricting motion from every direction, and the bottom ring is allowed to move horizontally at the rate of 0.05 millimeters per minute in the x direction. The bottom surface of the ballast is restricted in y direction. The normal load is applied to the surface of the ballast as pressure. Penalty interaction was defined with suitable frictional coefficients. The figure shows the shear stress variation of ballast along x direction at 3 planes: middle plane of the top ring, center plane of the whole assembly, and the middle plane of the bottom ring. The graph in the left shows The shear stress was shear strain of fresh ballast during experimental and numerical analysis. It can be observed that during the application of 30 kilopascal normal pressure, the experimental values tally with numerical model analysis results with a considerable accuracy. And during the application of 90 kilopascal pressure, experimental results and numerical analysis results tally only after gaining 6% of the shear strain. It is observed that the shear strain is increasing with the vertical pressure, and this behavior is obtained during both experimental and numerical analysis. The major deviation between numerical and experimental results during the application of 60 kilopascal and 90 kilopascal can be due to the discrete nature of ballast and voids, which cannot be captured by the continuum model of ballast. Figure in the right shows the shear stress strain behavior of ballast when ballast is contaminated with 5% clay. The shear strength of the ballast is reducing during the analysis of experimental results. The clay particles act as a lubricant between ballast particles and reduce the friction between ballast. This leads to reduction of shear strength. Likewise, the behavior of clay foul ballast is captured by altering the material properties during the numerical simulation. The figure shows the shear strain variation of ballast fouled is 15% sand when the normal load is increased. When the sand is mixed with fresh ballast, the overall weight and density of ballast increases. Therefore, the Young's modulus and the ballast increases with the fines percentage. Accordingly, the material properties of sand-fouled ballast were altered to achieve the real material properties of sand-fouled ballast. A parametric study was done using the numerical model. After validating this model, shear stress and behavior of ballast mixed with 10% and 15% sand was analyzed by increasing the normal pressure up to 120 kilopascal and 150 kilopascal. The figure shows the shear stress and behavior of sand-fouled ballast with 15% of sand weight. It is observed that with the normal load, shear stress has also increased. Another parametric study was done by changing the fines percentage by observing the experimental and numerical results of the sand-fouled ballast with 10% and 15% weight sand. Then the material properties was determined for fouled ballast with 20% and 25% sand weight. Young's modulus was increased. The shear stress was shear strain behavior was obtained under vertical pressures of 30 kilopascal, 60 kilopascal, and 90 kilopascal. It is shown in the figure. It is observed that when the fines percentage is increased, shear strength is also increased. These are the conclusions of the research. The large-scale direct shear test can be simulated on fresh ballast, clay-fouled ballast, and sand-fouled ballast using the developed finite element model. The validated numerical model with sand-fouled ballast can be used to predict the shear stress strain behavior of sand-fouled ballast with increased normal pressure. Also, the model can be used to predict the shear behavior of ballast when the fines percentage is increased by using carefully determined material properties. I would like to appreciate the support provided by the Ehad Depression University of Peradeniya for this research. These are the references of this slides, and thank you.